Hello and welcome to Pale Blue Pod, the astronomy podcast for people who are overwhelmed by the universe but want to be its friend.
It's true, and I'm one of them. I'm Corinne Caputo, a writer and funny person and friend to almost everybody, I think, in the universe.
Yeah, I agree. Everyone who deserves it, at least.
But I have one enemy, and I can't. No, I'm kidding. I don't. And I won't reveal who it is.
Ooh, intrigue. Hello, everyone. I am Dr. Moiya McTier. I'm an astrophysicist and a folklorist and a friend to the universe and most of the people in it. I do have an enemy. I have an arch nemesis.
Oh my god, I gotta know who it is.
You do. And I will tell you, I'm very vocal about the fact that this person is my arch nemesis, and maybe I shouldn't be, but that's okay, because Pale Blue Pod isn't big enough for this to have any bad consequences. I personally know that my arch nemesis is Jimmy Fallon.
Wait. Same.
Wait. Really?
No.
Oh,
I can just
damn
decide
it.
that. But I don't know if I can say this. My husband did write for The Tonight Show for many years, so I probably need to stay neutral. But I love where this is headed and fully support.
Jimmy Fallon's Twitter bio just says astrophysicist, and it makes me so angry. For anyone who has ever seen the movie Clue based on the game, that scene at the end where Mrs. White is just like, flames, flames on the side of my face. I'm so angry. That's how I feel about Jimmy Fallon calling himself an astrophysicist.
I love it.
That's also how I feel about Jimmy Fallon stringing me along for 8 months and then not making my TV show, but whatever. It's
wow,
fine.
Moiya. All right, we'll talk off pod about this.
But now you all know who my arch nemesis is.
It's out there. And
It's
you know
out,
what? He knows.
It's out into the universe.
He
It is,
knew.
because I went very mini viral back in 2020 when I posted a video on Twitter, back when Twitter wasn't awful.
I remember this.
But I was like, Jimmy Fallon, you cannot call yourself an astrophysicist. I will teach you, and then you can call yourself an honorary one, but no, we gotta fix this right now. Mm-hmm. He did not respond.
I remember you tweeting that.
Oh, well.
I think it's for the best.
I agree. So, I mean, I don't know why we're starting this episode with such animosity, even though he deserves it. But today,
Let's get it out.
We're getting it out, yeah. So that for the rest of the episode, it's just good vibes. And we are feeling those good vibes at the 50-yard line of your local football field.
I love that we're here, but I do want to know why.
We're here. It's the middle of the day, middle of the football field. We can hear birds around. There's wind going by, but it's pretty peaceful. And we are here because it's another scientist bio episode. And this scientist was very into marching band, and I was very into marching band. And so I just wanted to honor that connection we had to her.
Oh.
Corinne, did you ever do marching band?
I didn't. My younger sister did and loves it and was like a really big, she was part of a drum corps for a few years.
Ooh.
And she has since gone back to like her high school every summer and kind of helped coach
Aww.
up and coming high schoolers in their band. It's where she met her fiance. It's like a big soft spot for it in our family.
That's so cute. Yeah, I started playing the clarinet in 4th grade and then joined marching band in 6th grade, which is earlier than most people are allowed to join.
I was going to say that's young, yeah.
It's young, but my friend Anna and I, Anna's the same person who did the illustrations.
I was going to say, is this Anna from your illustrations?
Mm-hmm. We were the banner carriers that first year, so we carried the banner that said, like, West Green Marching Band in front of everyone, and then I did marching band for the rest of my time in high school, and I loved the structure of it. It's like a sport, being out there.
It is.
In the heat, under the sun, just marching in formation for hours at a time. Like, it's a workout.
My sister's team, especially when she was in drum corps, was like really long days, really hot days, probably or certainly not getting enough water and nutrition that they needed for the duration and endurance they had to do.
Yeah.
She was like ripped too, muscular wise.
Yeah.
She was like
in the drum
really
corps. Yeah, the drum corps people and the tuba players, the sousaphone players.
Yes. She was on the Cadets, which was like a Pennsylvania group. And they had like people from all over like parts of the East Coast of the U.S. She taught herself, she had played clarinet in her high school marching band, but she taught herself mellophone because they had an opening for a mellophone player, and she wanted to be a part of the corps.
Oh,
Very
nice. When you do marching band, you have to memorize music and play it while you're walking, often very close to other people who have instruments that can hit you. And so you learn a lot of skills. You learn how to multitask. You learn good memory skills. You learn good physical situational awareness. Like you learn a lot. And so I am not surprised that this woman, this brilliant woman we're talking about today, also was in the marching band, because it turns you into quite a character.
It does. She was great.
She was great. You know the drill. This is a scientist bio episode, which means we are talking about someone who is no longer with us. For this person, Dr. Beth A. Brown, that is especially sad. She passed at a really young age. She was only 39. But that means that I'm even more honored to get to talk about her and, share her legacy with all of you today.
Yeah. I can share a bit about her early life.
Yes, please.
So she was born on February 4th, 1969.
Oh, good year.
Yeah. Because of 69.
Not because of that.
Because we went to the moon.
We went to the moon. Yes.
She's born on February 4th, and she grew up with her parents. She has a younger brother and an older cousin in Roanoke, Virginia. And from what I learned about her online, her curiosity for science began with, I think in a way that a lot of us get interested in things, which is through TV shows and movies. So she was really into Star Trek and Star Wars, which I love, to not pick a side. She's both.
That's what I was going to say. Usually you're one or the other. Interesting that she didn't choose.
I think it's probably just so exciting. Like, if this is piquing what's going to be your lifelong interest, then absorb it all. So in elementary and in junior high school, she was really into science, and she explored these by participating in a lot of school science fairs, the way that we kind of had to as kids. But apparently she never did a science project on space. It was more of just like broad science.
Respect.
And later, she would get into space. She moved up in high school. She took a few AP classes and played in the marching band. And a defining moment for her to pursue astronomy occurred on a class field trip where she observed the Ring Nebula and fell in love with the stars during a trip to an observatory.
Ooh, I like that.
AdvancingPhysics.org wrote a bit about this. She looked through a telescope and saw the Ring Nebula, and it was all she needed to get hooked on astronomy. And she's quoted as saying, "I thought it was just so cool to know that I was looking at something that was so unfathomable in terms of distance," which I do think is one of the defining moments for a lot of people learning about space, of like, wait, this is so big and so far away.
That's what got me into it, yeah.
Yeah. And I think it's what has made other people overwhelmed, like the purpose of this podcast, to combat. But I love that she was excited by it and not scared away.
Nice.
She graduated as valedictorian in 1987 from her high school.
Okay.
And then attended Howard University, where she studied physics and astronomy. And she also played the piccolo in the university's Showtime marching band.
Ooh, that's so high.
Yeah.
Good for her.
I don't know how close that is to clarinet.
I mean, in terms of pitch, it's much higher. It's a piccolo is like a tiny flute.
Oh, right. Mm-hmm. Well, it kind of sounds like a spaghetti noodle to me, and I love it.
Yes, all of those spaghetti noodles on the marching band team.
Yeah, famously.
Famous. Mm-hmm. We all have heard about those. We don't need to say anything more because we're all very familiar.
She has another quote. She says, "Space fascinated me. I was into anything that had to do with space. I thought actually being out in space would be the coolest thing possible."
Oh.
And I agree.
Yeah. Yeah. It's a shame that we can't find more information about her life and her influences.
Yeah, I feel like it's nice that there are so many people involved in space work that we don't have the kind of Sally Ride level books about all of them, but I still want that from everybody, but yeah.
Yeah, me too. But we did find a little bit. She did a couple of research projects in her undergrad at Howard, but I couldn't find anything about those. I imagine they were probably related to the research that she went on to do on elliptical galaxies and black holes. But we know she did a couple of research projects in undergrad at NASA. She did internships there. She graduated from Howard in 1991, and then she got her master's from the University of Michigan in 94, 93. And then she graduated with her PhD from the University of Michigan in 1998. And the reason that I really wanted to make an episode about her was because she was the first Black woman to get a PhD in astronomy from Michigan. Full stop. She was the first Black woman to do this, which makes her probably like in the first 10 on the list of Black women to get PhDs in astronomy in the country. I was number like 23, 24. So yeah, she's a pioneer. She is a vanguard in our field, and I wanted to make sure I talked about her. Her dissertation research when she was at the University of Michigan was on X-ray emission from galaxies. So she used the ROSAT telescope. That is not an acronym, but a portmanteau. It stands for, it's a shortened form of Röntgen satellite. Röntgen is the German word for X-rays, named after a German scientist. And so this is a primarily German, but a collaboration with the US and Europe. And it was an X-ray telescope sent into space. It was really good at giving you high resolution images. It had really good spatial resolution, so it could distinguish things that were pretty close together, even if those two things were really far away from us. So good spatial resolution, cool. But not very good spectroscopic resolution. If you were looking at the spectra of these galaxies, or if you were trying to figure out what molecules they were emitting, that would be a little blurrier. And it was really good for low surface brightness galaxies. So galaxies that don't shine a lot in the X-rays. Probably because it had a very wide field of view and could collect many photons at once. And this is especially difficult in X-ray astronomy. I did one X-ray research project in college. I was studying a quasar, so a very energetic black hole in a different galaxy. And when you're dealing with X-ray astronomy, you can count the individual photons.
Wow.
Like in my optical work and in my infrared work, like you're dealing with the intensity. Like you're just you're measuring how strong is the light beam that we get from this source. With X-rays, you're like, how many individual photons have I gotten from this source?
Wow.
So
that's specific.
Yeah. And so a telescope or a satellite that has a really wide field of view will let you collect as many photons as possible. Really important with X-rays. So for her dissertation specifically, she gathered a sample of 34 different elliptical galaxies. Unlike a spiral galaxy that is usually in a flat disk with that like swirly spiral arm pattern that the Milky Way has, elliptical galaxies are more spherical, so they're not as flat, and they don't have that defined spiral structure. I think of them as like little spherical balls of chaos. A spiral galaxy is held together by the motion, by like the rotation of the disk. You can't do that in an elliptical galaxy. It is held together by chaos. It's held together by the very almost random way that stars move around the galaxy. So those are ellipticals. And she was studying their origin, their behavior, and their evolution of the hot gas in elliptical galaxies because she wanted to understand how this gas cools down. This is at an interesting time in galactic astronomy. This is the 90s, so we understand roughly how galaxies evolve. We know that spiral galaxies will often collide, and what's left over is usually an elliptical galaxy. But we don't, at the time, we didn't totally understand what goes on during those galactic collisions. We didn't understand how the elliptical galaxy like settled into its final shape or like behavior, and a lot of what influences that is the temperature and the distribution of gas. Hot gas is very diffuse, it spreads out, and it's kind of hard to make anything happen, but it does glow brighter in X-rays, whereas cool gas will clump more. That's where you're going to get a lot of star formation, and star formation also produces a lot of X-rays. And so one of the big themes that you can see across all of her research is that she was trying to figure out, when you see X-rays from an elliptical galaxy, are those X-rays typically coming from all of the hot gas in the galaxy, or are they coming from all of the young stars and all of the energetic black holes? So trying to figure out which of those two mechanisms was dominant in these galaxies. So she took that sample of 34 galaxies and she measured their X-ray luminosities. So how bright are they in the X-ray part of the light spectrum? From those X-ray luminosities, she was able to calculate average temperatures of different regions in these galaxies. So is this gas hot, warm, or cold? And it's really annoying because different astronomers have different cutoffs for what makes gas hot versus warm versus cold. Like, no one really agrees on these temperature cutoffs. So if you're ever talking to an individual astronomer and they start talking about like hot versus cold gas, probably a good idea to ask them what they think is hot gas.
Sure, yeah, okay. Yeah. I'm sure I'll find myself in that situation.
Oh, I know. When you and all of the listeners inevitably find themselves in that scenario, please follow my advice. Okay, so she calculates the temperatures to figure out if it's hot, warm, or cold. And then she can separate the X-ray sources into the different buckets of, is this X-ray emission caused by hot gas, or is it caused by stars and black holes and other things that emit X-rays? It turned out, if you go through her dissertation, that for most of the galaxies in that sample, she couldn't tell what the dominant mechanism was, despite ROSAT's really good spatial resolution. She could determine the mechanism for some of the galaxies, but not all. So that's her dissertation. After she graduated in 1998, she worked as a postdoc at NASA. Actually, for the rest of her career, she was at NASA, but at different centers, either as a postdoc or as a researcher. She studied elliptical galaxies with supermassive black holes that shine in the X-rays using multiple different telescopes, ROSAT, like she used in her dissertation, or NASA's Chandra X-ray Observatory, which is another space-based X-ray observatory. The X-ray observatories have to be in space because X-rays don't penetrate our Earth atmosphere very well.
Oh, that's cool. I didn't know that.
Yeah, we have to send them up above all of our gross water vapor and stuff.
Yeah, get out of here.
So that was most of her research. She was also really passionate about outreach and did a lot of service for the community, which is very typical for women, especially women of color in academia. We are often asked to do more mentoring because if we want to have women and people of color come up in the field, it helps if they have an advisor or a mentor who can relate to their experiences, which means people of color, women, gender nonconforming folks, anyone who has a marginalized identity usually ends up doing more labor in academia that is unpaid and underappreciated. But she did a lot of it because she was a good person and because if she didn't do it, other people weren't going to.
Yeah.
So while she was at Michigan for her PhD, she gave a lot of planetarium tours and talks. She developed amateur stargazing courses that could be done without telescopes. You're in a city, and there's lots of light pollution, and you're dealing with a lot of people who don't have the resources to go and get their own telescope or travel to like a public one. So she developed this course of what you can see in the sky with just your unaided eyes.
Cool.
Which is important. She participated in a program at NASA called the Administrator's Fellowship Project, where she was given a year to go back to Howard University and develop an introductory astronomy course. She did. That course and the one that she developed at Michigan, both still taught today.
That's awesome.
Yeah. She developed a website for the multi-wavelength Milky Way project. She took data and images of the Milky Way in different wavelengths. So there's like a picture of the Milky Way in the optical, a picture of the Milky Way in the infrared. And she put that data and those images up on this website and made it accessible for people who hadn't really heard this information before. Again, this is back in like the early 2000s. Websites were kind of new and like a very exciting way to get information at the time. And so you can still go to the multi-wavelength Milky Way project website, but it's kind of defunct and they don't add anything to it anymore. But it is in the research notes for this episode if you join our Patreon. There were 10 different wavelengths that they showed the Milky Way in, and that's cool. Making this accessible to people who aren't going to comb through data archives or go to a talk at a university. When she passed in 2008, at 39 years old, which is very young. Mm-hmm. But when she passed, she had either just started or was about to start a job as the Assistant Director for Science Communication at NASA's Goddard Space Flight Center. So she was going to continue her legacy of doing a lot of outreach and SciComm, but didn't get the chance to make an impact in that way. And she did a lot of service, which is separate from outreach because you're not like talking to people about science, but you are facilitating other people doing and talking about science. So she was on the board of the National Society of Black Physicists, NSBP. She was also in some leadership role for the National Conference of Black Physics Students. Both of those organizations put together conferences for Black and brown students. Both of them will give out research and travel funding. They'll support people who are part of the community as they're going through this really difficult process of trying to get a PhD. Mm-hmm. And I found this quote that I really like. She was once asked what her greatest achievement was, and all of her research, all of her outreach, all of the really impressive positions that she held at NASA, out of all of that, she said that her greatest achievement was, quote, convincing a young woman not to give up on her dreams of becoming a scientist because someone had told her she couldn't.
Aww.
I've read that quote multiple times today, and it still just gave me chills. So,
yeah, that's really nice.
Yeah, she seemed like a good person, and when you read all of the obituaries and like memorial posts that different NASA sites and the American Astronomical Society and like other astro groups, the obituaries that they put up all said something to the effect of, she was a really lovely person, she's going to be missed, and like I know they always say nice things,
right?
But these had specifics about her being a very positive influence on the community, because she clearly was.
Yeah. I actually did pull a quote from NASA, one of NASA's tributes to her. I pulled a quote out because I liked it so much. It opened with, "She lit up a room with her wonderful smile. She made everyone in her presence feel that they were important. On October 5th, 2008, one of our rising stars in astronomy had fallen." It was so sweet and sad.
Yeah, and her death was really unexpected. She died in 2008 from a pulmonary embolism, so no warning, I don't think. But she has left behind a beautiful legacy. She leaves behind her research. She leaves behind people that she mentored. That young woman that she convinced to stay in the field, I'm sure, thinks about her often. But there's also a Dr. Beth A. Brown Science Foundation. It was started, I'm pretty sure, by her family, and it provides scholarships for students who are planning to major in astronomy or physics at university. And then there is the AAS, so the American Astronomical Society Beth Brown Memorial Award. They give it out every year to 3 recipients. It provides a free year of AAS membership, a free registration for one AAS meeting, and $1,000 to cover the cost of attending that meeting. So travel, lodging, food, whatever. $1,000 often not enough to cover the cost of going to a conference, but it's something. And then the winner, the recipient, also gets invited to give a talk about their journey into science at Howard and Michigan, and they'll pay for them to go out and give that talk, which is a nice legacy.
Yeah, that really is.
Mm-hmm. She seemed like a nice lady who did cool research and also had a positive impact on astronomy, like the people side of astronomy.
Yeah,
so.
Yeah, I'm sure that was much needed and maybe still is, but just kind of keeping people encouraged and optimistic.
Yeah.
Hi, it's Corinne. Moiya is grabbing snacks, so I'll take this time to thank our patrons, especially our Sun-like stars, Sharn Llewellyn, Lissa, and Peyton. And of course, you can support us, hear your name on this pod, and make it to our patron star chart, all by supporting us on Patreon for just about $1 per episode. If you sign up for an annual membership, you get a 13% discount, 1% for every constellation in the zodiac. Find the star chart, Patreon info, and more at our website, palebluepod.com, or by going right to patreon.com/palebluepod. And if you can't support us financially, that's totally fine. I still love you. Moiya still loves you. You are still space. Another great way to support us is to share the show with your friends. And before you go, if you are loving Pale Blue Pod, and especially if you're loving Dr. Moiya McTier, you have to give her other podcast, Exolore, a listen. If you didn't know, Moiya is also a folklorist. So if you've ever wondered about what life would be like on different planets or how writers create your favorite fictional worlds, Moiya has the facts for you. On Exolore, Dr. Moiya McTier explores fictional worlds by building them with a panel of expert guests, interviewing professional world builders, and reviewing the merits of worlds that they have already built. You'll learn, you'll laugh, you'll gain an appreciation for how special our planet really is. So subscribe today by searching Exolore on your podcast app or by going to exolorepod.com. Bye.
So that's about as much as I could find on her work and research, but I do have a little game for you, Corinne.
A game!
Yes, a little game. We are reprising our Is It a Paper game.
Is it a paper?
Where I read out a sequence of words that may or may not be an actual title of an actual paper written by Beth Brown. And Corinne tells me whether or not she thinks it's a real paper.
Oh, gosh. Okay. I'm nervous, but I'm ready to go.
For this one, I obviously have the title of the paper, but I also have a summary of the paper taken from the abstract. I did not read all of these scientific papers, but I'll give that information to you after you tell me your answer. We have 7 different titles here for you today. The first, Corinne, is Extraordinary Line-Emitting Knots in the Crab Nebula.
Whoa.
Yeah.
I don't think that's a paper.
Why?
I think the word extraordinary is throwing me off. It's like too happy.
It seems it's a bit like sensationalizing for an astronomy paper title.
Yeah, it's a little clickable, which I feel like is not usually the vibe.
You're right. It is not usually the vibe, but it was the vibe this time.
It was the vibe!
Extraordinary Line-Emitting Knots in the Crab Nebula is an actual article that was published in 1994 in Astrophysical Journal Letters. These are short little, almost like half papers that you can submit to the journal, and instead of being like a full peer-reviewed paper where you are kind of testing a hypothesis and rocking the scientific community with your new knowledge, these letters are like, we saw this thing but we don't know what it is, or we have added a new planet to the catalog. It's these small little findings that probably aren't worth a whole paper but still worth telling the community about. And in this paper, they talked about how they had been observing the Crab Nebula, and they noticed these knots, which are bright round spots in the image. They took that image with the Goddard Fabry-Perot imager. It's like hyphenated names. It's an imager at the Michigan/Dartmouth/MIT Observatory. And these knots, these bright circles in the image, they noticed that they were emitting a lot of argon and a few other elements and molecules, but like a lot of argon, and that those knots were aligned with the pulsar at the center of the nebula. So there's the Crab pulsar, which is left over from a star that went supernova, and the guts of that star resulted in the Crab Nebula. And later studies hypothesized that those knots were shocks caused by the pulsar jet. So as the pulsar jet is moving out into the space between stars, it encounters some dense area, and kind of like a traffic jam, it pushes all of the stuff in that dense area together to create like a shock wave as the material is moving through space.
Whoa.
Yay.
Yay.
And they're just saying hey, we've seen these knots. Everyone be
Noted.
aware.
Yeah.
Noted. Yes. All right, so that's number 1. Number 2, on black hole binary in spirals, X-ray radiation as solution to the final parsec problem.
I gotta say, this is a paper.
You think this is a paper? Why do you think this is a paper? Is it the
I
colon?
don't understand. Yeah, because...
Corinne, it's not a paper.
But you... Oh my god, you're just too good at the game.
I learned from last time.
You, Moiya, are too good.
Last time you got all of them right, and I was like, all right, I'll do better.
None of my tricks are working this round.
I knew I had to have one with a colon, because a colon makes it seem more legit.
Exactly.
It sounded like you were about to say this just all sounds like it makes sense together.
Well, I was thinking in my head, actually, that I have no idea if this makes sense together or not. But the colon makes me think it's a paper. But you could have written, gummy bears have taken over the moon, but in science words, and I would have been sure.
Now I'm writing it down. Gummy bears have taken over the moon, and I'm going to figure out how to put that into science speak.
Well, that's there's an old tweet that was how would you put that you changed a light bulb on your resume? And people are successfully implemented a new strategy for whatever. And I'm okay, yeah. You can make anything sound really good.
Yeah. Oh, I'm going to think on this. All of these are real things. A black hole binary in spiral is a real thing. It's relevant to our gravitational waves episode that we did before. When you have two black holes that are orbiting each other, they'll radiate away gravitational energy and get closer together, orbit each other faster, and we call that inspiraling. And there is a real thing, a real mystery in astronomy called the final parsec problem, where when you have two black holes that get to be 1 parsec apart, we aren't sure how they manage to radiate away that final little bit of energy. And so I presented a possible solution to the final parsec problem of inspiraling black hole binaries, and the colon made it seem real.
And you got me there.
I did. You're welcome. All right, this next one. Aligned spin orientation for elliptical galaxies in the Virgo cluster.
I think it's a paper.
Okay, why?
It just seems kind of plain.
It's just there.
It's just there. It's kind of plain to a person like me, which makes me think, okay, this is something professional and organized that's happening. And therefore, I think it's a paper.
It's not a paper.
Oh my god. Maybe the strategy is I just say everything's a paper until we get to a paper.
Maybe. I'm glad I got better at this since last time. I did try to make something that would sound kind of reasonable and in line with what she studied.
Sure.
So she studied elliptical galaxies, but she did not study the rotation of those elliptical galaxies.
Okay.
So I guess what I was trying to get at with this hypothetical paper was that there are a bunch of galaxies in the Virgo cluster that for some reason are all spinning in the same direction. And if we did find that would be fascinating. That would be worth a paper. But that's not a thing.
Aww.
I just have so much fun with these.
I feel like you could train an AI on these.
Oh, no, you could. But it already is scraping the internet for enough training data.
You know what?
So
You're so right. Never mind.
We don't need to add any more. Well, you are now 0 for 3. Maybe number 4 is a lucky one. Number 4. Construction of a Penrose diagram for a spatially coherent evaporating black hole. Listeners, Corinne's face is so priceless right now. You can see the thoughts moving through her brain.
I'm like, construction of a Penrose diagram.
Yes.
No idea. For a spatially coherent, no idea, evaporating black hole. Again, confused.
Again, no idea. So what was your answer?
I think not a paper.
This is a paper.
Oh, God. Of course, it was time. We were due for a paper.
This is from 2008. This is when you go to her publication site. This is the last publication listed. It was published in the journal Classical and Quantum Gravity. And it was her and her advisor, or like someone she worked with, putting together, going through the thought experiment of imagining the Penrose diagram for this specific type of black hole. So a Penrose diagram shows you the relationship between space and time around a black hole, and it lets you see how they have been distorted, because a more massive black hole is going to distort space-time differently than a less massive black hole. And a spinning black hole is going to distort space-time in a different way from a stationary one. And a black hole that has no charge will affect it differently. So like you get the pattern here. And we did an episode on black holes where we talked about scientists thinking about them in these really ideal scenarios, and then over time we got more complicated with it and we started adding more detail, like the charge or the spin of a black hole. So there had already been Penrose diagrams made for regular boring black holes, but Beth Brown and her co-author on this wanted to make that same diagram for this more complicated black hole, one that is evaporating away, so emitting radiation, Hawking radiation, which we talked about in the black hole episode, which means you have a Penrose diagram that is changing over time. So it's just like, it's cool stuff.
Cool.
Yeah.
That is cool.
Yeah. Not something that I am personally experienced or, frankly, interested in. I am not that into black holes, and I'm especially not into very complicated mathematical diagrams of black holes. But this is how Beth Brown chose to spend her time in the last year of her life that she didn't realize was going to be the last year of her life. And I just wonder, would she have done this had she known?
Oh, I wonder.
Probably. She seemed very into it.
Yeah.
But I'm just saying, I personally would not.
I would have traveled the world.
Penrose diagrams. All right, number 5. Measuring Itzenkrantz emission in low surface brightness galaxies.
Not a paper.
Why?
Because it seems like the same construction of the previous title, but with synonyms.
Oh, interesting.
Like construction of a Penrose diagram, measuring Itzenkrantz emission, obviously different, but like the cadence is the same.
Okay.
But if I'm wrong, then I think it is a paper.
I think the answer is whatever the right answer is. You're right. It's not a paper.
Yay!
Itzenkrantz emission is not a thing. I just made up sounds.
And you did well.
Otherwise,
I would have thought that was a real thing.
Otherwise, this very well could have been a paper. She was measuring different types of emission in low surface brightness galaxies. I just made up a type of emission. Out of curiosity, Corinne, just so I know what I can do next time, had I called it Doofenshmirtz emission, would you have caught the reference?
I would have thought that. Oh, caught the reference? No.
Or would you have known that I was making it up?
That name sounds more made up to me than Itzenkrantz.
Which is why I said Itzenkrantz instead of Doofenshmirtz.
Yeah, you made the right call. This Itzenkrantz feels like series of unfortunate events, but totally believable.
Okay, so that's fake. Congrats, you got one. You're on the board.
Yes.
Next one. The effect of environment on the X-ray emission from early type galaxies. Early type galaxies is another way of saying elliptical galaxies.
Not a paper.
Corinne, that is a paper.
Ah,
Why did you think it wasn't a paper?
I'm trying. I don't know.
All right.
I was like, I think that maybe the last one might be a paper, just based on pure gut, having
Just
no
like
idea,
the
having
pattern.
not read the last one.
Okay. This is a paper. This came out in the year 2000 in the Astrophysical Journal, and for this paper, she and her co-authors looked at, I think, that same sample of 34 elliptical galaxies and measuring their luminosities. And they found that there is a positive correlation between the fraction of X-ray brightness to total brightness. So there's a positive correlation between that and the local galaxy density. So in other words, when you have a denser environment in a galaxy, then there is more X-ray light than you expect compared to all light. And they were confused about why that might be. It seems that maybe when you are in a dense environment in a galaxy, the galactic winds are stifled, and those galactic winds are actually pretty effective at cooling down a galaxy. And when you have a hot galaxy, remember I said before, that hot gas emits a lot of X-rays, so without this cooling wind, you end up with hotter gas and more X-ray light than you expect.
Yeah, okay.
That was a paper in 2000.
So it is a paper. So it is a paper.
It is a paper. Yes. It's a
And now I
paper
believe
from when she was a postdoc. Number 7, our last one. Are you ready? I think you've got one right.
I have one right.
Okay.
And I'm sticking number 1.
This last one. Emission mechanisms in X-ray faint galaxies.
Paper. Simple, straightforward.
Simple, straightforward. Okay. It's a paper!
Yay! I got 2. Number 2.
2 out of 7 is good. It's respectable.
2 out of 7. Yeah. That's exactly what they told me in school.
So this is a paper in Astrophysical Journal from 2001. She examined the X-ray surface brightness profiles of 17 different X-ray faint galaxies. So when I say surface brightness profiles, I mean she measured the surface brightness of the galaxy at different distances from the center, so you could get a sense for how that changes. Does it get brighter as it goes to the edge of the galaxy? Does it get dimmer? Is there a weird peak or something? Mm-hmm. So she found that distribution, and she assumed in that research, because she was trying to, again, like, decouple the different X-ray source mechanisms, hot gas versus stars. And she assumed that those different mechanisms would have different profile shapes. That, we expect there to be more stars in the center of the galaxy, so the X-ray profile for those stars should be very high, close to the center, and then drop off as you go towards the edge. But for the hot gas, we expect that to be more evenly distributed, and so maybe it would be a flatter shape to the profile, for example. But ultimately, they found that their best fit for the stellar contribution of the X-rays was lower than other studies suggested. So if you were to take their study to heart, then you would assume that there's less X-ray emission from stars than from hot gas.
Okay.
Yes.
Cool.
But other studies disagree. So, and this was in 2001. And we have better technology, better telescopes and better data analysis software now. So maybe that has been updated, but I don't know of any updates on that work. But I didn't specifically focus on elliptical galaxies, so there's that. But 2 out of 7, congratulations!
Yay! A 28%.
Yeah, why not?
Love it.
Love it. Yeah. How do you feel about her papers?
Well, they seem like papers. Clearly, I was not great at predicting when it was a paper and when it wasn't.
No, I'm just really sneaky. I'm just good at coming up with
You're
fake
really
paper
good at
titles.
this game. I love her papers, and I think I just love that she was so enthusiastic and got other people enthusiastic about this. I think that's the goal.
Yeah, I agree. I'm glad she was around, and I'm glad that we got the chance to talk about her in this episode.
Yeah. Well, wherever you are, whether it's on this football field or at a marching band performance or just listening along, I hope you remember that you are space.
Yeah, you are.
Bye.
Pale Blue Pod was created by Moiya McTier and Corinne Caputo with help from the Multitude Productions team. Our theme music is by Evan Johnston, and our cover art is by Shay McMullen. Our audio editing is handled by the incomparable Misha Stanton.
Stay in touch with us and the universe by following @PaleBluePod on Twitter and Instagram, or check out our website, palebluepod.com. We're a member of Multitude, an independent podcast collective and production studio. If you like Pale Blue Pod, you will love the other shows that live on our website at multitude.productions.
If you want to support Pale Blue Pod financially, join our community over at patreon.com/palebluepod. For just about $1 per episode, you get a shout out on one of our shows and access to director's commentary for each episode. The very best way, though, to help Pale Blue Pod grow is to share it with your friends. So send this episode, this link, to one person who you think will like it, and we will appreciate you for forever.
Thanks for listening to Pale Blue Pod. You'll hear us again next week.
Bye.